I hope you can see that behind me. Can we kill the lights in the back? So it makes it a little easier to see. All right, so let's talk about this idea of the sample distribution. Let's go back to the idea of the distribution of the sample means. If you guys remember, just before the test, we were talking about the idea that we can have two kinds of normal distributions. We can have one normal distribution, which represents the actual population, the people in the population. For instance, their weights. Like, so for instance, this normal distribution you see on the screen or behind me, that could either represent, that might represent the weights of people in this population, the entire population. So the middle of this distribution, where the peak is the mean and the median. They're both, if it's a perfect normal distribution, the mean and the median are the same. This bell-shaped distribution is symmetrical, and all is right with the world, right? Assuming that that's the case. So let's say for our population, the distribution of weights is normal. Half the weights are below the mean, half the weights are above the mean. This distribution represents the range of values that you can have for the people in this population. The higher it is, the more people are represented by that. So you can see in the middle part of this, people, they tend to be more people whose weights are close to average than there are people whose weights are very high or people whose weights are very low. And the further and further out you go to lower weights and heavier weights, the fewer people in this population that have those weights. Okay, and that's the way normal distribution typically will shake out. Now, let's say that for this population, that the range of weights for, let's say, middle-aged adults is from 75 pounds to 375 pounds. And in the middle there is some value like 150 or something like that. So that doesn't sound very normal, but trust me for a moment on this. So the range of these values is very spread apart because we know that there are individuals that have very low weights and people who have very high weights. They're going to be in the tails of this distribution. Now, if I were going to say to myself, I'm going to go into this population and, I don't know what the mean is. I have no idea. I don't have the benefit of seeing this distribution behind me. And I don't know what the mean is. So instead, I'm going to sample this population because I can't afford to call up everybody in this population and ask them what their weights are. And maybe they'll lie to me anyway. I want to measure it. And I'm going to take a sample of 100 people from this population. Okay, so I take a sample of 100 people from this population. I take the average of that sample. The average of that sample is now my sample mean. Okay, in other words, I think that is going to represent approximately what the mean is. So that's what, that makes sense, right? You take a large sample size like 100, you randomly sample people in a population, you find the average for that sample, and you make the assumption, well, that's a good approximation of the mean. Okay, now in real life, when we do this, when we take a sample like that, we never know what the real mean is because we're never going to go out and do the entire population. The only guess that we have of what the mean is that mean for that sample. So that sample is what we call our point estimate. Okay, in other words, when I take a sample, 100 people, the average weight is 182 pounds. That is my point estimate for the mean. Okay, so, but it's an estimate, right? Half the time I will underestimate it. It'll be below the real mean. Half the time it'll be above the real mean. How do I know that? Well, I know that because they're going to replicate what the mean does. In fact, if I were to take a sample of size 100 over and over and over and over again and take all of those sample means and create a distribution like the one behind me, it's going to look very similar to this. It's going to look something like this. Oops, upside down. And let me click on that, and let's see what it's going to look like. It's going to look something like this. Not very pretty, right? It's going to look something like this. And what's going to happen here is the middle of all my sample means is going to be very close to what my population mean is. In fact, the more samples that I take, the closer it will be. And the other thing that's going to happen is that my sample means are going to be a narrower range than my population mean, right? Because I'm no longer going to have to display on my distribution that person who's 75 pounds or that person that's 375 pounds, because they're going to be averaged into a group of 99 other people. So all of my sample means are going to be closer to the mean than the way the population is distributed. And we know that the sample means, they have their own normal distribution. And we know that the standard deviation for those sample means is a special number that we call the standard error. And that standard error, that variability, is much narrower for the sample means than it is for the population mean. So for instance, in this particular case, if the population mean had been was 150, let's say, and the standard deviation for the population, again, something we'll never know, standard deviation for the population is 10 pounds. Well, what would be the standard deviation for all the sample means? Well, we know that we discussed last time we got together that the formula for the standard deviation of the population mean, of the sample means, in other words, the thing we call the standard error, is going to be the standard deviation for the population divided by the square root of the sample size. So if the population standard deviation is 10 and our sample size is 100, then our standard error is 10 divided by the square root of 100 is 10, is going to be equal to 1. So that shows you how much narrower that distribution is going to be. What if that sample size had only been 25 instead of 100? What would my distribution now, what would my spread be, my standard error be for my sample means? It would be 10 divided by the square root of 25 this time, which is only 5. So now it would be 2, right? Well, what about if it had been, say, 4? Right? My sample size had been, instead of 25, my sample size had been 16, right? Well, now it would be 4 into 10. So it would be 2.5. So see what's happening here? The smaller the sample size we have, the more spread out my sample means can be. So my standard error, the value of my standard error really depends on two things. Depends again on the population standard deviation, and it depends on the sample size. The bigger the sample size is, the narrower is my distribution means. Okay, so I'm going to take advantage of that now. I'm going to take advantage of that by saying I can't afford to take over and over and over again samples of size 100. So what I'm going to do is I'm going to take one sample of size 100, right? And I'm going to say, okay, let's say that it came out to be 148, right? Well, I may not have gotten, let's assume for a second that I got the mean absolutely correctly. It really is 148. Well, I know that 95% of the time, if I went back and sampled this population again, it would be within 2 standard deviations of the mean. Now, the standard deviations of the samples is equal to sigma over the square root of n. For 100, that's going to be equal to 10 over 100. Sigma is equal to 10. That's going to be 10 over a square root of 100, which is going to be equal to 1. The standard error is going to be equal to 1. So I know if I go 2 standard errors to the left, which is going to be 146, and 2 standard errors to the right, which is going to be 150, right? I know that if I'm right about that mean being 148, 95% of the time when I go back and take another sample, it's going to be between 146 and 150. Right? Because that's what the standard error tells me, 2 standard deviations below and 2 above. But it also tells me that 2.5% of the time, it's not going to be within that group, right? 2.5% of the time, I'll get the wrong answer for the mean, right? It'll be either too low 2.5% of the time or too high 2.5% of the time. Total of 5% of the time, I may be wrong. Okay, so we're going to take advantage of that now for us to understand, by doing only one sample, to understand how precisely or how accurately or how well we can rely on our measurement to predict what the mean is. And the way we're going to do that is we're going to take advantage of the standard error. So I'm going to give you an example right now without going to anything we're going to do in the book. And I'm going to say to myself, okay, I'm going to take a sample. I'm going to take this population, the standard deviation of this population. We need to know that, don't we, in order to do this, or we're dead in the water, right? Okay, well, there's a couple of ways we can know that. One way is I can tell you. The other way is, let's say that I take a sample size 100, sample of size 100, and I say, let's see, the mean, I'm going to call the mean now of that sample X bar. I don't use mu when I'm looking at a sample mean. It turns out the mean is equal to 100. Maybe it's blood pressures this time. Okay, the mean is equal to 100. Well, I know what the mean is. I know what the sample size is. And I want to know what I can predict about other samples. But in order to do that, in order to calculate the standard error of repeated samples, I need to know what sigma is. Sigma over the square root of n is the formula. I know what n is, right? So I took the sample. So how am I going to know about that standard deviation? For the first few problems that we work on tonight, I'm going to tell you what the standard deviation is. I'm going to tell you that in this case, the standard deviation is equal to 20. Okay? One other way we might know what the standard deviation is by just simply taking the same 100 people that we have weights for, that we use to get this average of 100, and calculating the standard deviation for them. In other words, the standard deviation of the sample is a good approximation of the standard deviation of the population, just like the mean of the sample is a good approximation for the mean of the sample is a good approximation for the mean of the population. The only problem with doing that is that we're trying to figure out what our uncertainty is about the mean. So if we apply another number which has a built-in uncertainty, like the standard deviation based on our sample, because we know that's not going to be exactly right, if I use that, I add another element of uncertainty. There's a way that we adjust for that. But we're not going to worry about that right now, because for right now, I'm going to be telling you what the standard deviation is. Okay, so in this case, standard deviation of the population, for some reason we know it. Could be that somebody did a similar study a while ago, took a gigantic sample, and has a really good idea of what the standard deviation. Maybe we know it from a population survey, like a census or something like that. But let's say now that our mean is 100, right? Our mean is 100 for our sample, and our standard deviation is 20. So our standard error is going to be equal to 20 divided by the square root of 100, which is 10. It's equal to 2, right? So I know that 95% of the possible other samples I might take are going to be between two standard errors below, 96, and two standard errors above, which is 104, right? So I can also kind of turn that around. I can say to myself, well, I don't really know what the mean is, right? But based on this, I think there's a 95% chance that I'm within two standard errors of the mean. So instead of looking at this as all the different possibilities that I would get for samples, look at it instead as a range within which you can say with 95% certainty, I think the true population mean is between here and here, between 96 and 102. 95% certainty. And we're going to call that, we're going to give that a name, we're going to call that the confidence interval. Not surprisingly, we're going to call this the 95% confidence interval. Now, let's say I want to be 99% confident that I make this range so that I capture the true population mean. Does this range have to be narrower or wider for me to increase my Yeah, I need it wider for me to increase my level of confidence, right? So it's got to be wider. So 99% confidence, you remember that we said that you had to be 3 standard deviations apart? So in other words, now I'm going to look for a range that's more standard deviations apart than before in order to call this. In other words, it'll still be 100, and I'll subtract, instead of 2, I might subtract 6 and make it 94 and make this 106. So now I am more than 99% certain that I've captured the true population mean. What if I'm willing to be less certain? I'm willing to be 90% certain. Well, now I can have a less wide interval. Okay, and how do I calculate how wide that interval needs to be? I calculate how many standard errors apart that I have to be in order to capture 90% of the outcomes. In other words, only have 5% in this tail and 5% in this tail. We haven't done that using the empirical formula. It's not an even number. That's why we haven't done it. But we're going to go to tables, and we're going to use the same number over and over again to actually calculate this. So now what I would like to do is let's actually apply this to something practical. I'm going to open up on Blackboard. There's 2 exercise sheets. I think I called it exercise sheet session 7, exercise 1, and session 7, exercise 2. Let's open those up and actually give them a try. Oh, somebody's got their camera on. Hi. Okay. Did we get a comment there? Okay, no problem. I closed it on my end. Okay, good. Let me just make sure we're muted here again too. Okay. Who was that, by the way, who had their camera on? Is it still on? I don't see it. Is it reduced? Oh, you guys can see it. I closed it on mine. Isabella, we can see you munching on something there. You Okay, good. We certainly, you're very pretty. We're glad to see you, just not right now. Yeah, it's closed now. Thank you. It's okay. Actually, to tell you the truth, that's less of an issue than not muting, because if you don't mute, then it winds up wind up with an echo. Okay, so on the recording anyway. Okay, so now I'm gonna open that up. I have to get to it myself. You can get to it on Blackboard. And I'm going to start with exercise number 1 and see where we stand. Okay, so exercise number 1, we're going to start a little slowly on this. Okay, the distribution of the number of eggs laid by a certain species of hens during their breeding period is 35. With a mean of 35, that's a mean of 35 eggs with a standard deviation of 18.2. That's a big standard deviation. Suppose a group of researchers randomly samples 45 hens of this species, counts the number of eggs laid during their breeding period, and records the sample means. They repeat this 1,000 times and build a distribution of sample means. Would you expect the shape of this distribution to be symmetric, right skewed, or left skewed? Now, remember we talked about something called the central limit theorem, where we said that even if the population distribution is not perfectly normal, if you were to take repeated samples and then drew the distribution of all the sample means, like 1,000 different sample means, what would that look like? That would be symmetrical, right? That would be certainly more symmetrical than the population mean is, right? So that's an important tool for us. Calculate the variability of this distribution of sample means and state the appropriate term to use to refer to this. Okay, so now we have, let's see, 35 eggs. They have a standard deviation of 18.2, and we're going to randomly sample of 45 hens. So our sample size is 45. Our standard deviation for the population is 18.2. So our standard deviation for all of the samples, repeated samples, is first of all going to be called what? Our standard error, right? And what is that standard error going to be equal to? 18.2 divided by the square root of 45. Solid number. I'm not going to bother to calculate that right now. Okay, suppose the researcher's budget is reduced and they are only able to collect a random sample of 10 hens. The sample mean of the number of eggs is recorded, and we repeat this 1,000 times, build a new distribution. How will the variability of this new distribution of samples be compared to the variability of the original one? Well, what's going to happen? Smaller sample size, smaller square root of n, bigger standard error, and it's going to be more widely distributed, the sample results. Okay, good. So kind of reinforce what we just talking about before. Okay, now I'm going to skip this one to tell you the truth. I'm going to go over to the next document, and I'll come back to those other two examples. Okay, you have a sample size of 100. Your sample winds up having a mean of 160. Assuming the population normally distributed has a standard deviations given to you of 30, compute a 95% confidence interval for the mean of that population. Okay, so what did we say we needed to know? We needed to know, number one, we're going to take the mean of the sample, which is x bar. I can't draw the bar very easily, so I'm going to say x bar, and I'm then going to take the standard error, right? Well, what's the standard error? The standard error is equal to, in this particular case, the standard error is equal to the standard deviation 30 divided by the square root of the sample size, which is 100, which I'm going to go in and change that to 10, and it's going to be equal to 3. So now I know that my sample mean is equal to 160, right? So 95% of the samples, my 95% confidence interval, is going to be two standard errors on the either side of that, right? So it's going to be equal to 6 taken from 160, was 154, and 6 added to 160, which is going to be 166. 95% confidence interval is going to be 154 to 166. We got a problem though, okay? And the problem is that the empirical formula is an estimate, right? The empirical form is an estimate. The real standard error that represents a 95% confidence interval isn't quite that neat. So I'm going to look it up right here. I'm going to figure out what that is right now. I'm going to go into the Z table. And in the Z table, we remember that the numbers in the middle represent the areas of the distribution. The numbers on the side and top represent the Z-score, right? So I'm going to look for the area that gives us only 2.5% in the lower tail, because that's going to be the Z-score that I need. I know it's going to be around 2, right? Because 2 is my estimate for my empirical formula. So let's look here and see where 2.5% is. 2.5, 2 point, let's see, 2 point, this is 3.8, 2 point, you notice that as I go across, it goes lower, 2.5, 2.50, that's 2.5%. What Z-score represents 2.5%? 1.1, 1.96. The number one, it's not really 2, is it? It's 1.96 standard deviations or standard errors that represent minus, subtracted and added, that represent, that number of standard errors represents the true 95% confidence interval, more accurately certainly than 2 does. So when I go back to this, I don't know why that came up. Okay, when I go back to this, let me get back to my notepad there. Okay, let's go here. Okay, oops, that's the wrong one. So when I go back to this and I take a look at this, well, in reality, my 95% confidence interval, okay, confidence interval, what is that going to be equal to? It's going to be equal to x bar plus or minus, did something happen up there? Can you see that? Maybe I'll scroll up a little bit more. And maybe I'll blow it up a bit too. Okay, it's going to be equal to x bar, the mean of my sample, plus or minus, well now instead of 2, I'm going to say 1.96 times my standard error. And in this case, what is that going to be equal to? That's going to be equal to 160 plus or minus, plus and minus, both, because it's going to go both directions, up below the mean and above the mean, 1.96 times, and what did I calculate my standard error to be? It was 3. Okay, so let's calculate that right now. So that's going to be 160. Let's see, plus, and what does that work out to be? 1.96 is 5.8. 5.82. Am I right? 5.88. Okay, plus 5.8, and it's going to be 160 minus 5.88. Or in other words, it's going to be, actually I should have put the negative number first, but that's okay. It's going to be 165.88 and comma 154.12. That look right? Okay, now normally just the way I would normally describe that is to put the lower number first rather than the higher number. It's just the way I accidentally laid it out there. That's my 95% confidence. I'm 95% certain that the true mean of this population lies between those two numbers. Okay, let's say that I wanted to be 99% certain, right? What's going to happen there? Well, it's still X bar, plus or minus, the standard error, but this time instead of being 1.96, what number are we going to use for the multiplier of standard error? Let's think about this. 99% confident means that we have only 1% chance of error. And since we have two tails, we could be too low or too high, it only have half of a percent or 0.005 in either tail. Let's go take a look at our table again, our Z table again, and see what would satisfy that. Okay, here it is. So 0.05. Okay, so it looks like it's somewhere around here. It's going to be 2.5, 2.5, somewhere around here, 2.6, 99%, half a percent, 2.5, 2.58, 2.57 or 2.58. Looks like it's halfway between. We're going to call it 2.58. So now what would that mean? That would mean I would go back here for my 99% confidence interval. When I calculated this, it's going to be X bar plus 2.58 times my standard error, which is still 3, right? Okay, and what is that going to be equal to? It's going to be equal to 160. Let's see, plus, what's 3.3 times 2.58? It's going to be 7.5 plus 7.55, was that 574? Am I wrong? What? 7.74. Okay, and it's going to be 160 minus the same amount. Since I'm adding 7.74 and subtracting 7.74 to 160 to get that range, my confidence interval and my range within which I think the real mean is, how about we give that another name? That range, the standard error times that number that we're using, 2.58 for a 99% confidence interval, or 1.96 for a 95% confidence interval. Let's call that combination number, the number that we're subtracting and adding to the mean. Let's give that a name. Anybody know what the name of that is? Margin of error. There you go, right? Kind of sounds like a margin of error, right? So that's our margin of error. So we add and subtract our margin of error, or standard error times the multiplier for the standard error times either 2.58 for 95% or 1.96. Now, what if I wanted a 90% confidence interval? What would I use instead? I'm not going to bother you look it up on the table, but anybody have looked it up already? 1.64. Smaller number, smaller margin of error, right? Smaller range, right? Smaller range, you can tolerate a smaller range because you're willing to accept more chance of being wrong, of missing the true mean. Okay, so this is how you calculate your confidence interval. And this confidence interval is very powerful. We'll apply it a couple more times. After observing 25 randomly selected caseworkers, the supervisor noticed that an average number of cases carried by each worker in a week was 50. From a previous long-term observation, it is known that the standard deviation from the entire department is 9 cases per week. Calculate a 95% confidence interval for the mean number of cases per worker per week for the entire department. In other words, the population mean. Okay, so how would we calculate that? What was X bar here? Anyone has a guess? What's X bar? What's our sample mean? 50, right? And what is our sample size? Sample size is 25, right? And what is our standard deviation? Sigma. Our population standard deviation. From a previous study, they know it's 9, right? So our 95% confidence interval is going to be equal to mean, right, which is 50, plus or minus our margin of error, which is going to be equal to, for 95%, 1.96 times, let's see what we have here. We have, what was it again? It was 9 divided by the square root of the sample size, which is 25, right? So it's going to be equal to 50 plus or minus 1.96 times 9 over the square root of 25, which is 5. 9 over 5 is is going to be 2.25, right? 2.25. So it's 1.96 times 2.25. Did I make a mistake? 1.8. I'm sorry. Yeah, oh, you're right. 1.8. 5 into 9. Yeah, 1.8. Yeah, good point. 1.8 times 1.96, and that's equal to 3.53. I'm going to call it. Okay, so I add and subtract that from 50, and it gives me my 95% confidence interval. If I want a 99% confidence interval, what's the only thing that changes here? That 1.96 becomes, for a 99% confidence, becomes what number? 2. Right. And for a 90% confidence interval, it becomes 4. Right. Good. Okay. Great. Right. Pretty easy, right? Okay. Now we're going to start to talk about why this is such a valuable thing. Let's do one more of these. Suppose you would like to estimate the mean amount of money spent on books by Hunter students in a semester. We have in this course nothing, right? Because we open source textbook, right? Okay. It used to be like 250. We have the following data, and the textbooks were not great. We have the following data from 100 randomly selected Hunter students. The mean amount spent, X bar, is equal to 249. That's from our sample of 100 randomly selected students. The standard deviation is equal to $30. Now, that standard deviation came from our sample. It introduces a certain amount of uncertainty now, doesn't it? Because before, we knew the population standard deviation. Now we're estimating the population standard deviation based on what the sample population standard deviation is. There's ways for us to to deal with that. However, we have a cheat. And that cheat is, if we have a large sample size, we're going to assume that we have a pretty good handle on what the population standard deviation is, and we're just going to go ahead and use this same formula. What's a large sample size? It could be as small as 30, greater than 30. In this case, 100 is a big sample size. Okay, so I'm going to ignore the fact that I know there's a little bit, I don't really know the population standard deviation sigma, so I'm going to use this standard deviation instead. And my justification is that it's such a big sample. 100 people is a big sample, right? So, okay, so the 95% confidence interval for the average cost of all books for students is going to be equal to, it's going to be equal to 249 plus or minus, and I'm going to 1.96 times, our standard error. What's our standard error? Well, our standard deviation was 30, and our sample size was 100, So it's 30 over the square root of 100, which is 10. So it's equal to 3, right? So, and I'm going to let you guys go ahead and calculate that, right? You'd count, it's roughly 6 below that, or about 241, comma, 250, let's 6 above, 255, right? A little bit off because it's going to be 1.96. And again, if I asked you for a 90% confidence interval, you would just use 1.64 in place of this. If I asked you for a 99% confidence interval, you would 2.58, and that 2.58 would make this a wider interval, make the margin of error bigger. You'd subtract more, add more, so it would be a wider range, right? So you're more confident, you're 99% confident that within that range is a true population mean. Okay, so now let's say that we wind up with a sample that's pretty small. Let me see what do we do in a case like that, where we don't have a sample that's big enough? Before we get into that, let's talk about proportions. We can apply this. Remember, we started to talk about that Galton machine, the one with the little balls that came down, and half the time we go to the left, half the time we go to the right. Basically the same as flipping a coin. Literally the same as flipping a coin. When the ball goes all left turns, it's as if you got all left heads. If you go all right turns, it winds up all the way down here, it's as if you got all tails, right? But you notice that overall it formed something that looks like a normal distribution. It's not really a standard normal distribution. It's what we call the normal approximation to the binomial distribution, right? Because that particular outcome is only yeses and nos, right? So yeses and nos can apply to a lot of things that we study. You have a disease, you don't have the disease. You had an improvement, you don't have an improvement. Many other things like that. So diabetic, not diabetic. So at any rate, so binomial distributions are important to us. So it's nice to be able to approximate them as a normal distribution. So let's give this a try here. Okay, so we had a voting situation. We were talking about voting before. We have an exit poll of 1,000 randomly selected voters and found that 535 favored the incumbent candidate. What did the other 465 do? They voted for the other. They were favored the other guy, right? Now the 1,000 is that, it could be, let's say this is a center. It could be millions of votes cast, right? So this is a poll. This is a sample of only 1,000 people. Okay. So in this case, 535 of them were going to vote for the incumbent. So what's the probability that any individual here would vote for the incumbent? What's that probability equal to? I'm gonna insert a page break here, so I got a little bit more room to work with. Right, 535 out of 1,000. What's the probability any individual in there is going to vote for that candidate? Oh, I can't get this to stop numbering things. Here we go. I hate when it auto numbers. Even when I hit you. Okay, I'm not going to worry about that. So P is going to be equal to probability that they're going to vote for the incumbent, any randomly selected individual, is going to be 535 divided by 1,000, or as you said, 0.535, right? 0.535, right? That's our probability, right? Okay, so now I'm going to call that P cap, right? I don't know what P is. I don't know what the true population proportion is. Population proportion I'll call P, right? Just like I called the population mean mu, right? I'm going to call the population proportion, but P cap, my estimate is going to be, my sample proportion is going to be 0.535. That's my point estimate. In other words, right now, just by looking at this number, I estimate that that candidate's going to get 53.5% of the vote, or 0.535 out of every 1,000, 535 out of every 1,000. That's what I think the outcome is going to be based on the mean. Now, the thing is that when we take a sample of 1,000 people, we may have the bad luck to get some. Well, first of all, number one, we know it's not going to be exact. right? When they go to the polls and they actually, everybody, all million people vote, it's not going to come out to be exactly 500.535 or 53.5%. It could be lower than that, could be higher than that. We could get hit by lightning, and it could be exactly that. We don't know. So in statistics, the best that we can do is at least quantify our level of uncertainty. What range do we think that, what range do we know, what range can we predict with 95% certainty the real outcome will be, the real percentage is going to be? We're never going to know 100%. The only way it's going to be 100% is if I say that the confidence interval is 0 to 100%. Right? That's not, that's meaningless, because then, basically saying we have no idea. So we think it's going to be 53%, but we don't know it for sure, right? So we want to know what's the range? What's the confidence interval for this? Is it 40% to 60%? Is it 51 to 53%? If our 95% confidence interval is 51% to 53.5%, I'm kind of saying I'm 95% certain that this guy's going to win, right? If my 95% confidence interval is 49% to 53.5%, well, now, I'm not 95% certain that he's going to win, because I'm not, that 50% of the vote is within that 95% confidence interval. He could be less than 50% in the vote and wind up losing. So let's calculate what our confidence interval is. So in order to calculate a confidence interval, I need to use, since it's 95%, it's going to be 1.96, right? I'm going to assume that this is a big enough sample. I'm going to talk about that in a second. Our sample size is equal to 1,000, right? So I'm going to assume that my number of standard errors is going to be 1.96. Now I need to know what my standard error is. So what's my standard error equal to when I have a proportion? Anybody remember what the formula for that is? It's the square root of P times 1 minus P divided by N. Square root of that whole thing. A little bit neater, if I could write it on more than one line, it would be P times 1 minus P over N, and take the square root of the whole thing. Okay, so what is that equal to in this case? That's equal to 0.535 times what's that? 465, right? Is that 1 minus P? Right? Yes. Do I have that right? 65, 30, that's right. Okay, divided by the sample size, which is 1,000. And now I have to take the square root of this whole thing. Okay, so let's calculate that. Okay, here's my calculator. Okay, so it's going to be equal to 0.535 times 465. Oops. Try again. 0.535 times 0.465. That's equal to, this is the top of our numerator, top of our fraction, and that's going to be divided by 1,000. And that's equal to 0.0002. Am I done? Got to take square root of it, right? And somewhere in here, I guess that's my square root right there. The square root of that comes out to be 0.0, I'm going to round it, 0.016, right? Or approximately 1.6%, right? So I'm going to call it 0.016, I'm going to call that, I'm going to round it off, is equal to 0.016. Let me see if I can't get that all on the same line. Standard. I'm going to bring the standard error down here so we can see it. Okay, so let's calculate our 95% confidence interval. It's going to be equal to P cap plus or minus, right? It's going to be, let's see, P cap plus or minus 1.96 times our standard error. In other words, it's going to be equal to 0.535 plus or minus, plus or minus 1.96 times 0.016. Okay, and let's figure out what that's equal to. Let's get the lower number first. Okay, you guys want to do the calculation? What is the lower number going to be? It's going to be 1.96 times 0.016. What's our standard error? I'll write down our standard error first. Plus or minus, plus and minus. What's that number going to be? 1.96 times 0.016. I gotta make it loud for me to hear it. 0.031. Can we round it a little bit? Okay, and let's see. So what is our lower number going to be? Our lower number for the confidence interval is going to be 0.5. Let's see, 3, it's 504, and our height 504, and our higher number is going to be, we're going to add that now, 0.566. In other words, we're 95% sure that the true proportion of people that are going to vote for this guy are between 50.4% and 56.6%. Is he going to win this election? What do you think? Yeah. How certain are we that we're going to win this? At least 95% certain that he's going to win this election. Okay, I'm going to show you something interesting now. Now, let's say we're doing a poll right now for let's say Hillary Clinton and Bernie Sanders, right? There's undecideds, right? So Hillary, the P cap for Hillary, I didn't spell that wrong, I think, is equal to, let's say, 0.35. And P cap for Bernie is equal to, let's say, 0.32, right? And there's a lot of people are still undecided, right? Actually, I'm gonna make her just to make them different. I'm not making any predictions here, but I'm gonna make it just to make them different. 0.55 and 0.32. 0.55 and 0.32. Okay, so if I were to calculate my standard error, I would get a different standard error for Hillary and for Bernie because they got different proportions, right? And then when I added and subtracted, I would get a different standard. I would get a different margin of error because I'd take 1.96 and so on and so forth. Well, gee, that's kind of a pain in the butt because, you know, I don't particularly like that because I'm going to get a different number for both of these. Well, the way they deal with that in polls is if I were going to calculate my standard error again is equal to, my standard error is going to be equal to 1.96 times my, my standard error is going to be based on my based on what my estimate of the standard error is. And the standard error for a proportion is going to be equal to P cap times 1 minus P, right? And I'm going to put this in parentheses. I put all this in parentheses, divided by n, and find the square root of this whole thing. Right? So what number would I pick for P that can make that as big as possible? What would be the biggest number? Well, 0.5. Excellent. If I make this 0.1, anything I take, and when I multiply 0.1 times 0.9, right, it comes out to be 0.09, right? If I make it 0.3, 0.3 times 0.7 becomes 0.21. If I multiply it 0.5 times 0.5, if I make it 0.5, then 1 minus P is 0.5. That gives me a number 0.25 on the top. That's the biggest number you can get. That's what they do. They don't bother to use the real proportions for each individual candidate. They use 0.5 for all of them. That's why you see a poll that says, oh, Bernie Sanders, this number over, Bernie Sanders, 36% of the vote, plus or minus 3%. Hillary Clinton, 10% of the vote, plus or minus. That's how they get all the same percentages for all of them. They take kind of a worst case, so they get an even percentage, so they don't have to have people calling them up. Well, how come the percentage is different for this person and this person? It's the same poll, and that's the reasoning behind it, because it's easier to take the worst case than to have to worry about, a debate over whether or not you really should have had a narrower confidence interval for one candidate versus another. But that's why you see it written that way. Once again, I drifted. What was her name? Can't think of it right now. It'll come to me. Mae West. Mae West used to say, "I was pure as snow, but I drifted." So at any rate, I kind of drifted there a little bit. Nice day. Now, surprising to get snow again, right? Disturbing to get snow again, I should say. Okay, so you have a number of other examples there. Okay, so I want to give you guys a chance to do one on your own. So let's see. Now, oh, by the way, you may have noticed, before I gave you a chance to do one on your own, you may have noticed that in this proportion, I didn't bother to worry about how big the sample size is or whether I knew the true population standard deviation. Because whenever we work with a proportion, one of the assumptions that we make is that we have a sample size of at least 30. But not only that, but also that on either side of the binomial, you have a sample size of at least 15. So in other words, even if you're looking at a population that has only 1% diabetes, well, then you have to have at least 15 people in your sample that have diabetes in order for you to use this method, and produce a confidence interval, right? And you could have whatever number in the other proportion, but you need at least 15 in each group. So if you have two binomial, you have two groups, by definition, you're always going to be over 30 if you have 15 in both groups. So we don't worry so much about the idea of whether or not we know the population standard deviation for proportions, because we're going to always be working with a larger sample size. Now, the other thing I want to point out to you is what happens if you have a small sample size and you don't know the population standard deviation. In that case, instead of using the formula that we were using before, instead of using this formula which said, so if I can't find somewhere to write here, I'm going to go back to Notepad. Okay. Note. Okay, I want to get rid of this thing. Okay. Okay. So my formula, as you saw up on that slide before, my formula for the 95% confidence interval is going to be X bar plus or minus 1.96 times the standard error. And my standard error is going to be equal to sigma over the square root of the sample size. Well, now, if we have a small sample size, I'm willing to do this also. If I don't know what sigma is, I'm willing to say standard error is equal to the standard deviation of the sample over the square root of n, but only for a large n, for a large sample size. Okay? And so what happens if we have a small sample size? Well, now, instead of using this number 1.96, what is that number really? That's a z-score, right? Instead of using that number z, x bar plus or minus z for 0.02, 0.05% times standard error, right? That's really what we're doing there. I'm going to use something called a t-score, okay? And x bar plus or minus the t-score for the confidence interval that I want, for, let's say for 0.05, 0.055% chance of error, okay, times my standard error, right? But my standard error is my standard deviation divided by the square root of n, even with a small n. So t, what do you think about t? Since a small sample size is going to give us a level of uncertainty, is the t value going to be bigger or smaller than c? Smaller than 1.96. Remember, we want to make up for the fact that we have less certainty. So in order to still say we're 95% certain, our interval has to be bigger. So this number is always bigger than 1.96, unless the sample size is infinite, is gigantic, right? So where do I look that up? I looked that up on another table, a t-table. And I think I put that on Blackboard, right? Almost 99% certain. T-table, yes, I'm sure. I took this. Okay, and how does this work? Well, take a look at this table that we're looking at here. I'm going to blow it up a bit. Okay, if you look at the top here, it says confidence interval, and it says right tail probability. In other words, in the tail, what's the size of the area in the tail of the range of values? It's 2.5%. Well, there's two tails, so this is for a confidence interval of 95%. So if my sample size is 25, what will I use instead of 1.96? Well, it's a dirty little secret over here, and that is that in this column, they don't give you the sample size. They give you something called degrees of freedom. One of the ways you might kind of, as a construct in your head, think about degrees of freedom. If I have one number, how many degrees of freedom do I have for that number? None. If I have two numbers, how many degrees of freedom? You got one. If you have 10 numbers, you have 9 degrees of freedom. It's typically the sample size minus 1. So if I have a sample size of 25, the number of degrees of freedom is 24. So I go down here to 24, and I go across to the column for the 95% confidence interval, and the value for t is 2.064. So if my sample size is 25, for t, instead of using 1.96, I would use 0.064? I think it was. Yeah, I think that's what it was. Times the standard error that I calculate. Okay, so this makes my confidence interval a bit wider. Okay, and similarly, you have a similar t-score, t-value for 90% confidence and 99% confidence. Okay, but the t-score, if I take a close look at this, let's take another look at this. If I take a look at this, how big a sample size do you need in order to get down to 1.96? Oh my goodness, look at that. I don't know if you can see it there. 1.96, you see it there at the bottom? 1.9, what's the sample size there? It's infinite, right? Very large sample size. On a practical basis, once we get over a sample size of about 30 or 40, it's so close to 1.96 very frequently, especially on first pass, we might not even bother to do this. That's why when we say you got a sample size of 100, well, that would wind up being like 1.99 anyway. So why not just use 1.96 and not bother with the table? Now, SPSS, when you do this same thing in SPSS, and next week we'll get a chance to do some of these problems in SPSS, or maybe when we go over I'm going to try and set up something so that we can spend a half hour maybe going over the answers to the problems on the exam that many people got wrong, right? That tended to be the same problems. Maybe we'll spend 5 or 10 minutes calculating a 95% confidence interval using SPSS. Well, it saves everybody a lot of grief, right? Because it happens like that. I'm going to try and open SPSS now. I won't hold my breath here because it may take the next 20 minutes to open. But that's another thing. I know you guys are having the same issues with the newer versions, operating systems on the Mac, and the most current version of SPSS. Kind of a little pain in the butt. I'll see if there's any updates or anything like that. When we use SPSS to do it, you'll actually be able to have them calculate it for you. So at any rate, the t-score that you use is going to be based on the sample size. And SPSS, we as a convenience, we say if it's a very big sample size, just use 1.96. But SPSS doesn't have to do any more work to look it up than it's already doing. So it always uses the t-score. If you gave it a sample size of 1,000, it would use the t-score for 1,000, which might be 1.96001 or something like that. It won't. It'll just do it, use it with the full accuracy that it needs, where you can maybe kind of cheat a little bit on very big sample sizes. Before I go any further, any questions? No questions? Got to be some questions, no? Right? Let's see how the guys online are doing. How are you guys online doing? Can you do this without the Z table? Yeah, we can do it with Excel, right? The Z table is another version of norm dist and norm S dist in Excel. We could certainly, if I pull up Excel, and we can, it'll open up well certainly a lot faster than that thing does. Okay, let's see. Let's go to 200%. Okay, so if the mean is 160 as one problem we had, and we use 1.96, right, and so on and so forth, and actually, we really don't even need the Z table if we're doing it that way. You do need the T table. Now, I'm not sure if the version of, let's see, t-test. Oh, there is a version of t-test in here. Array 1, array 2. Yeah, there's a problem with that. T-dist. Okay. All right. Let's see. X, degrees of freedom, and tails. I'm not sure what X is. So what else I got for T? T distribution, T test, T inverse. Inverse. Probability, degrees of freedom. Okay, T inverse. Let's say I want to know what the T value is for 95%, 0.95, for a sample size of 15. Degrees of freedom would be 14. Let me see if this works for me. The t-score is 0.063. Nope, that's not right. T inverse, probability. Let me see. T-score. 0.95. That's the probability. I have to take a look at it. I shouldn't have gotten it. It's been a while since I've used Excel to do t-tests. There actually is, like on the PC version, there is you can add in a package, a statistical package, which does a lot of other functions besides the built-in ones in Excel. That'll help you do t-tests and a lot of the other tests that we're working on. I don't think it's universally available in all the different versions of Excel. There's an issue with some versions don't have Microsoft Basic available, which I think it runs in, or something of that nature. So I won't worry about that right now. But you can certainly use Excel to do the calculation. 1.60 plus or minus 1.96 times whatever your standard error is calculated for and stuff like that. In fact, which probably makes a lot of sense because it's going to be harder to make an error. Now let me see if this ever opened up. Is it still bouncing around there? No, it stopped bouncing and it didn't open. Oh, that's discouraging. Yeah, like I said, later on in the week, I'll schedule something and I'll do a video on SPSS and maybe a little of this as well. I'll see if I can't work out something with those Excel functions. Let's see what another way I can do this. Is it starting up? No, it doesn't seem to be up. It thinks it started. You know, it's going to pop open any second now. Could be a memory issue. Move things out of the way just in case. And start it that way too. Okay, guys, it's 8:50, so I'm not going to hold you here. I'm going to hold my breath here and see if this doesn't start up. It will eventually, I know that, but I don't want to keep you here while this is doing that. And you guys online, if you want to hang around for a few minutes while I see if I can't get this going, you're welcome to. But if it does start up, I'll have it on the video that I'll post tomorrow. Okay, so good night, guys. Okay, so you're okay with this? You get the idea of how we're going to use this? Oh, look at that. Look, it rose from, how could it possibly, you know how many operations are going on in this computer every second, right? What could it possibly be doing? This is a very old program that's been bought and sold a number of times. IBM is the most recent owner of it. And they update it very frequently. The problem is that they never rewrite the whole thing from scratch. You know, so whenever they don't really keep up with the technology that we have around now. So, I don't know what this is written in, if it's written in C or COBOL or who knows what it's written in, but they never really rewrite it from the ground up. So there's always issues with it being very slow or crashing and so on and so forth, especially when you're using a newer version of it on a newer operating system. Okay, and you guys, there are plenty of other problems there they can use on those exercises that you can use for practice. And I'll put together an answer sheet for it too, so you know whether or not you got them right. How about the test? Anybody have a particular question on the test? I know there were some stumbles on the diagnostic test because it got a little, you had to do a little bit of interpretation. Like if you looked at it first glance, you might have not realized that the diagnostic test was in the rows and the outcome, disease or no disease, was in the columns. It looked like you were dealing with two tests, right? So, but the outcome, because she told you that the gold standard test was in the columns, that basically means that everybody that was in the left column was a smoker. Everybody who's in the right column was definitely not a smoker, right? And the diagnostic test you were testing was the one, the self-reported smoking. You were testing to see how reliable that test was of just asking someone, are you a smoker? What do they do, insurance companies now? Insurance companies, they do any kind of testing, or they just take your word for it?
Oh, who knows?
Yeah. Yeah. They don't do many.
Well, I don't think it would be something like the nicotine test. I was just reading that. I was like, this is just getting people up to like correct.
Oh, there you go. Right. They might not be smoking.
Nicotine in other ways.
Yeah.
Like
yeah.
patch or something.
Yeah.
I'm sure there's a test because there's also, I've looked at dental hospitals too, where they don't allow smoking.
Right.
Like smoking tobacco.
Yeah.
So they drug test you and I think.
Oh, maybe a urine test or something. Well, then they probably do a nicotine test, I would think. Right?
But then that would include people who are trying to put smoking into like cigarette gum.
Yeah, but that kind of person is called a smoker.
Well, right, but that doesn't mean they're actively smoking cigarettes.
Yeah, that's true.
It just means they're
yeah. So or they're vaping. I was in Paris in October, and there's a vaping store on every other corner there, because they smoke like fiends.
Yeah.
I'm serious. I mean, there were cigarette butts everywhere. Yeah, Europeans, especially French, Parisians especially, smoke like fiends, and they're all trying to quit. And they're literally. I think I've only seen one or two here. These little vest pocket, vape stores or whatever they're called. But they were all over the place. They were all over the place, and they were selling like a million different kind of gadgets and different forms of it, flavors, and so on and so. It's a whole nother industry.
It is.
Yeah. Yeah.
Turns out.
Well, that's what cigarettes were anyway, right? A nicotine delivery device. That's really what all they were.
Really?
Yeah. Well, I mean, well, nicotine's really the thing that's really addictive,
Right.
right? So I think that's
Yeah,
what.
but it's like, I would say like habit.
Yeah, it's habit also, but nicotine all by it's physically addictive.
Right.
It really is. So I mean that's really as far as the cigarette companies are concerned. The cigarette is a nicotine delivery device, a way to satisfy their addicts. Take care. Good night.
Have a good night.
Okay, let me see what I can do here. Smokers. Oh, here's the amount of weight gained. The North Carolina study. Here's the amount of weight gained. And if I go to the data view, we can see that in the data view gain, the amount of weight that each pregnant woman gained. This is a sample, even though it's a very large sample, 800 people in this, is still a subset of all the births in North Carolina during the course of a year. There might have been 30 or 40,000 or 50,000 births during the course of that year. So I'm going to use this sample to estimate what the mean amount of weight gained by women in North Carolina is during the course of that year. So I'm going to go up to Analyze, Descriptive Statistics. Now, since I'm looking for a mean, I'm going to go into Descriptives, and I'm going to say, okay, weight gain during pregnancy. Okay, and I'm going to ask it to give me the standard deviation, the mean. I don't care about. I might as well ask her for the range. And I'm going to say okay and get the result there. So the 800 women in this, at least the ones that reported their weight gain, right? 777 valid results in this. Had a range of 95 pounds from 0 pounds to 95. I'm not sure what that's about. It may be that that was a typo or something like that. Perhaps 95 was right, maybe not, but maybe it was a typo also. So that was the minimum and maximum values. But the average value was 30.58, and the standard deviation was 13.65. Okay, so now that gives me the variability of the actual sample. So now I can use this standard deviation because it's such a large sample as an estimate of the population standard deviation. And the standard error of the mean is going to be the standard deviation divided by the square root of the sample size. So the standard error is going to be a much smaller number. In fact, I'm going to go back up here. I'm going to analyze. I'm going to go, oops, I'm going to go to analyze. I'm going to say, where did I had something that just disappeared there. Analyze, descriptive statistics. This I'm going to go to explore. I'm going to click on explore and I'm going to put the weight gain during pregnancy into my dependence list. Okay, the number that I'm going to analyze. I'm going to go to statistics and it's already going to checked off that it's going to do a number of descriptive statistics for this numerical variable. So I'm just going to go ahead and say okay. SPSS is going to recalculate that mean. In fact, we'll see it again here. In fact, here is the mean again. The mean for weight gain during pregnancy was 30.58 pounds. And the standard deviation was 13.65. So now my standard error is going to be my standard deviation divided by the square root of my sample size, which was 777. So that gives me a standard error of 0.49 pounds. So I add and subtract 1.96 times 0.49 pounds, or whatever the p-value would be if it's a small sample. So I add and subtract that from my mean, and I get my 95% confidence interval, which SPSS does calculation for me. And my I am 95% certain that the value for the mean of weight gain in pounds for this population is between 29.62 and 31.54. Okay, I'm going to do one more interesting thing. I'm going to go into Analyze, and again, I have to get to this. For some reason, it changes my table. selections. Explore. And this time into the factor list, I am going to put the marital let's see, smoking status of the mother. So it's going to factor this into two groups, women who smoked and women who didn't smoke when it does all these calculations. I'll click OK, and let's see where we wind up this time. And as I said, it's going to factor this into two groups. Okay, the first group is mother did not smoke during pregnancy. That's the average weight for that group, and our confidence interval 29.64. And the other one is mothers who did smoke during pregnancy, and there's a confidence interval for that group, 27 to 33 and 29 to 31. This is a much narrower range of confidence, probably because the sample size is so much bigger for women who didn't smoke when they did the calculation. And to tell you the truth, these numbers overlap quite a bit, 29 to 31 and 27 to 33. So I'm not even really sure there is that big a difference between the true mean weight gain for mothers who smoked versus mothers who didn't smoke. The actual means was 30.19 and 30.65, the actual means for the sample, that is. Okay, so that gives you a look at the how we might handle these problems using SPSS. The SPSS also gives us our box plot. You can see with side by side. Doesn't look like much difference between these two groups. Okay, so you guys online, good night, and I'll try and get this posted as soon as I can. Bye.